All right, today I want to talk about the outer planets. These were visited by several satellites NASA flew. First is the Voyager satellites. They flew 2 satellites, launching them in 76 or so. And they took magnificent pictures. The second mission is the Cassini mission that we've already spoken about. And I'll show you a few pictures from each mission. First of all, of course, you know something about the planets. These are the right sizes. This is the Earth, and it's very small compared to Jupiter, Saturn, Uranus, Neptune. Okay, the question is why? How big is this? What is it made of? What can we learn about the galaxy, about the stars, about the planets by studying these objects? All right, first of all, why are the Jovian planets so different? All these were formed beyond the frost line. That was something I drew on earlier figures. Remember, the frost line means that the temperature is less than freezing, and a frost is formed there. That's a temperature that is about 5 astronomical units from the Earth. Everything that far and further is got with the first sun that heats it up. The frost does not melt. Now that means that there's a lot of ice. The ice is solid in those temperatures, and it allows it to form planets, big planets, which are made mostly of ice. The moons especially are made of ice. Very strange. Okay, now this is also, they're far from anything, and allows the planets to capture hydrogen and helium, which the inner planets could not do. So they each formed a miniature solar system, formed moons. And here's an example. Here is the whole solar system forming, and here's a little piece of it forming, and it looks just like the big one. But this might be Jupiter. It forms a miniature solar system. Exactly the same. And this is rotating in a certain way, and the small clouds, the small vortices in the middle of the aggregate have to rotate the same way also. So it's not surprising that Jupiter has its planets and its spin all oriented in the same as the solar system and the disk. All right, here's Jupiter. This is the red spot. These are magnificent bands. Why are there all these bands on Jupiter? Well, it's because of the zonal winds, all by centrifugal force, which diverts the streams and makes the winds. This might be eastward, that's westward blowing, etc. These dark spots are the result of a comet strike on Jupiter. They don't last very long. They're temporary dents on Jupiter's outer clouds. We'll show those later. I'll tell you, those are from a satellite, a broken up comet we call Kohoutek, and I'll show you more about that. And of course, here's the red spot. All right, so this is Jupiter, the giant in the solar system. Its radius is 10 times that of Earth. Its year takes 12 years to orbit around the sun. And that's according to Kepler's law and for the distance of Jupiter. Remember that the orbiting time of the planet around the sun is not dependent on the mass of the planet. It only depends on the distance of the planet from the sun. The mass does not enter this. Okay. It's 318 times the Earth mass, and that is determined by applying Kepler's third laws to the Galilean planets that orbit it. It's the same way that we determine the mass of the Earth or the mass of the Sun, by orbiting around and seeing how long it takes. Okay. And the mass is 1/10 of 1% that of the Sun. Now, this Jupiter is actually a failed star. If it were any higher, it would be a real star. Actually, a star burns, we call a star anything that has 0.08 times the mass of Jupiter. If 0.08 times the mass of the Sun, excuse me. If Jupiter were 8 times more massive, it would be a star. And we'll talk about the stars of that category later. Okay, so the day is only 10 hours. That means the thing really rotates fast. And it rotates fast enough that it makes the planet oblate. What do I mean by oblate? What shape? Yeah. That's right. And what's the difference between that and prolate? For example, football, except for the tips on the end. What's a football? Is that oblate or prolate? Huh? Prolate. Footballs are prolate. But a planet that's spinning if this is the round Earth, because of the spin of the Earth, it makes the planet a little fatter. This is the North Pole. Here's the South Pole. Okay. The equator is a little bit fatter. And this rotates around, and you can see that, you think about it, if it rotates around, this looks like a football on this picture, but it's not a football when you realize in 3 dimensions it is squashed. Okay, I don't know of any sports that use oblate balls. Another sport uses prolate balls. What's this? The sport? Huh? Rugby. Yeah, rugby. Right. Okay. So you know that the furthest point from the center of the Earth is not Mount Everest. It is a mountain here in what is it? Ecuador or somewhere. Ecuador is on the equator, and there are some mountains that are measured only to be 14 or 18,000 feet. I don't remember what it is. 18,000 feet, I think. But it's the furthest point from the center of the Earth when you include the oblateness of the Earth. All right, why is the Earth oblate? Anybody? Because of the spin. Okay? It's only round if it's not spinning. And the oblateness of Jupiter is very extreme. Very extreme. So it's oblate. Okay. Density is just a little bit above water. And this, of course, is much less than the density of the Earth, which is averages to be 5 grams per cubic centimeter. Okay. All right. Again, it's composed of hydrogen and helium. But there's no surface to Jupiter. It looks like there's a surface, but that's just an optical depth, like there's a surface to a cloud. It is really just a gigantic cloud. If you fall on Jupiter, you'll keep falling and falling and falling into the center, hotter and denser, but nowhere is there a surface. None at all. It's a gas giant. The sun doesn't have a surface either. Okay. But in the center of Jupiter, it does have a surface, and we'll talk about that very briefly. And the colorful bands are bands of ammonia, sulfur, and all kinds of stuff. All right, their zonal winds are really strong, and that's the Great Red Spot. It's considered to be a storm, a storm just like a hurricane is a big storm on the Earth. But this hurricane has lasted for 300 years because Galileo noted it. Or not Galileo. His telescope was too poor. People who came a little bit after Galileo and looked at Jupiter noticed of this big red spot. Same storm as now. Okay. Okay, so here's what Jupiter looks like. No solid surface, and these are liquid. This is what it is. On the outside, the temperature 125 degrees rapidly climbs up to 20,000 degrees toward the center. The pressure in terms of bars, remember the 1 bar is the pressure of the Earth, 14.7 or 0.2 or 0.5. What's the pressure of, anyhow, one bar is the Earth's pressure, and the pressure goes 1/500,000, 100 million in the center. That is pretty high pressure. You get squeezed flat. Okay? The density goes very low density up to very high density. It goes 25 times the Earth's, 25 times grams per cubic centimeter. 25 grams per cubic centimeter, which is very much higher than the center of the Earth, which is only 8 grams per cubic centimeter. All right. All right, so the temperature increases, and this core, of course, here, the rock and metals, is bigger than the entire Earth. Okay, and it's so dense because of the gigantic pressure from all the stuff above it, and the moon. Oops, let's go back. There's all this funny stuff: liquid hydrogen, metallic hydrogen. That's some stuff we never can find. Metallic hydrogen is very hard to make. Requires a very high pressure above it to make it. It is not natural. Yeah?
What's metallic hydrogen?
Metallic hydrogen is it's hydrogen in a form where the electrons are free to move about. I mean, what is the difference between a metal and non-metal? Say copper compared to a rock. What is the difference between them? The difference is that copper is a structure where the electrons of copper are not bound to an individual atom. The electrons can move from atom to atom to atom. They move easily, and that allows them to conduct a current. So the fact that they move so easily makes it something called a metal. The fact of a rock, it doesn't support a current, meaning that the electrons are very tightly bound to atoms individually, and there's nothing you can do to move it. So that's what defines an insulator. It doesn't conduct electricity. But that's all solid-state physics. So we're not going to do that in this course. Okay. All right. Now, because Jupiter is pointed up, and then orbits like this, it doesn't, or spins up and orbits like this around the sun. It's always the same every year, every day. So there are no seasons on Jupiter. Giant magnetic field. And the magnetic field means that there's some liquid in Jupiter. Something liquid. The metallic core, the metals above it are all liquefied. And that's what you need to have a giant magnetic field. And this is very interesting. Jupiter, now the planets like Earth have a simple law that the radiation the planet gives off is equal to the radiation it receives from the sun. The Earth has no source of energy. The interior heat of the Earth is locked away because it's the thermal conduction of the rock is miserable. All right? So in Jupiter, though, it radiates 2.5 times as much as it receives from the sun. What the hell does that mean? Well, what it means is that Jupiter is giving off some of the residual heat with which it was made. The residual heat is all the rock coming together, crashing and banging, heats the inside, and also the radioactivity that's in the material decaying and giving heat. So the heat flows up in Jupiter. It doesn't have a rocky crust like our planet, and it flows out, shows up as temperature increase. Jupiter has a higher higher output than input. All right, that drives convection, etc. Saturn also puts out 2 times as much heat as it receives from the sun. Okay, all right, now the zonal winds on the Earth, I told you about them. They're known as, these happen to be known as Hadley's cells, after Mr. Hadley, who did the original work on this subject. We have eastern winds along the equator. Further north and south, you have westerly winds. That's what we have here. Further north again, north or south again, you have easterly winds. So these 3 zones are due to our rotation. If we're rotating faster, we would have more zones, 5, 6, 7. All right, and if you rotate as fast as Jupiter, you have 12, I don't know what it is, 10 or 12. A lot of zones, doesn't really matter. Okay. Now, Jupiter has a magnificent magnetic field. Here it is. This is a picture of it. It's drawn there, and here it is here. Now, that's the aurora borealis. I can't remember the aurora. It's just the aurora. All right, for the same reason that we have an aurora. It's because the magnetic field is way out here, and the charged particles that come in spiral around the magnetic field lines and bang on the planet at the poles. All right, now, Jupiter also has many, many spots that are smaller than the red spot. Okay, here is a blow-up of the aurora of Jupiter. Rather pretty picture. Okay, this is actually not Jupiter, that's Io. Io is a moon of Jupiter. And the question is, what the hell does a moon do with all this magnetic field? That must mean that Io is liquid. Io is liquid, but it's no bigger than our moon. How can an object that's smaller than the moon actually be liquid today? It doesn't make sense. How does Io do this? How is that? All right, the moon, we know that Io is constantly ejecting material. It's really active. It has volcanoes on it. And the volcanoes spit out material that goes into space, volcanic gases. The gases are really complicated stuff. They're heavier elements, sulfur, oxygen, sodium, and they form this donut shape around Io. Okay, that's all right. And they help, anyhow, they're there, and they form bombardment to the atmosphere of other planets. So let me show you a little bit how this works. Okay, now I'm going to tell you first about the Voyager missions. 1987, when were you born? 1977. You were born in the 80s, weren't you? Oh, Jesus. All right, so the Voyager mission was over by that time. So you didn't hear all the excitement when that happened. They launched in 97. There were 2 missions, and it hit or got to Jupiter in 79, Saturn in 1980. 2 missions, though. They launched 2 because they really weren't certain that it would make it. That it would go all the way, and they didn't want to lose the whole thing, so they launched 2 as a backup. One was the backup of the other, but both of them made it. So we got some beautiful pictures. Okay, now they deflected Voyager 1 out of the plane of the solar system. Let's say this is the plane. Voyager 1 went a little south on Saturn, south, and then it got kicked way up high. All right? And Jupiter and Voyager 2 was used Jupiter to hit it on the side. I'm sorry, Saturn to hit it on the side, deflected it toward Uranus, went on the side of Uranus and deflected it toward Neptune. This is kind of incredible. The planets were amazing because you deflect off Jupiter, goes right to Saturn. Deflect off Saturn and go to Uranus. Deflect off Uranus and you go to Neptune. Now, the planets are not usually lined up so perfectly to do this. The astronomers knew that there was a time when the planets would be lined up, and you could do it in the 1970s. It was possible to do it, and they did it. It doesn't happen that often, and I don't remember how often it happens. All right, now this was again a nuclear-powered spacecraft for the reasons we talked about, and they're so far out they're going to drift forever, and they're going to become they become junk in outer space, and some other civilization will pick it up, and they'll look at it and realize that Earth, this planet had intelligent life to make this thing. Of course, it's pretty primitive by their standards, but it was intelligent nonetheless. All right. Unfortunately, these things are not going very fast. It'll take forever to get to another star. So it's just outside the Earth's center. Okay. Now, what did they find? First of all, they found that all the planets have magnetic fields. Here's Jupiter, Saturn, Uranus, Neptune. Remember that the flux of the light of the magnetic fields decreases. The flux of the high-energy particles coming from the sun, here it goes. It's not as dense out in Neptune as it is in Jupiter for the same reason. Light's not as intense. It's just diluted by the distance. Okay. All right, they have weaker magnetospheres further out, and that tells us the fraction, electrical conductivity is weaker, solar wind is weaker. All right. Okay, and we don't actually know why these are molten, but it doesn't matter. Okay, so here is Io. This is a vision taken by Cassini a long time ago. Here's the red spot, and here is the shadow of Io on Jupiter. Now, remember Cassini went to Saturn, but on the way out to Saturn, particularly when it got slungshot by Jupiter, they decided, of course, we're close enough, let's take some pictures. This is a picture. All right, so I'm going to break for a moment here to show some Jupiter's giant. Okay. Oh, Jupiter. Okay, now, this is a movie taken by time-lapse, taken by pictures day by day by day. All right, so it's not going to be steady, and but nonetheless, it's very interesting. Let me move this back. Okay, now watch the red spot and watch the clouds around it. The clouds are moving. Isn't that pretty? The clouds all move relative to the red spot. So these movies were lined up. Each time they lined up the red spot. so you can see the clouds. So this shows you that Jupiter is not really fixed. It is, those clouds are moving that you're looking at, just like clouds in the Earth move. You can't take a picture and expect it to be the same the next day. All right, let me go back. Look at these spots. 1, 2, 3, 4. They're little storms. So everything's moving on Jupiter. Just a second. All right, well. Okay. All right, next, let's take a look at the 4 moons of Jupiter. These are the Galilean moons. In the sense that Galileo could see these in his tiny little telescope, and you could see them on our small telescope as well. Who has seen? Oh, Jupiter's not up now. Jupiter is seen in the day when it's daylight, and so it's not a visible object, which is too bad, because these are magnificent to look at. All right, so 4 prominent moons. There are several other smaller moons, but these are 4 prominent moons that Galileo could see. Io is the first one. It has volcanoes, lava, sulfur, fumes, and Io is known as the pizza pie moon. If you like your pizza pie, here you go. This looks like sort of a pizza pie with sort of a melted, yucky yellow cheese on it, just like they make at Lavelle's. A hideous pizza, in my opinion. You know what it is? Oh, all right. We have a little conflict there. I think it's made with yellow cheese, isn't it? Okay. All right, fine. Oh, well. Anyhow. And it's got little toppings. I guess those are olives or pepperoni. All right, the next moon is Enceladus. Okay. All right, now Io is a mess. It's changing tidal forces, and I'll tell you what we mean. Not Europa, is smooth. This is Europa. There are very few craters on it. And we suspect that Europa does have a magnetic field, which means that something is liquid in the planet. The only suggestion for what could be liquid is water. Water, there's a frozen surface, and underneath it is an ocean. We don't know the exact how deep it is, but it might contain life. All right? We don't know. Okay, Ganymede is the next planet. This is Ganymede, and it's the largest moon. There's lots of craters and grooves. We'll look at it a little later. And then Callisto is the 4th moon out, and it's very heavily cratered. And we'll see what the surfaces are. All right, now, I've already told you the answer to this. The moons of Jupiter are geologically active. Okay, and the question is, why is it geologically active? That seems really hopeless to explain. All right. Now, first of all, you'd say, wait a minute. The moons are way too small to allow active geology. But the terrestrial planets are made mostly of rock, of course. The Jovian planets are made mostly of ice. A whole planet made of ice, or mostly ice. And the ice melts at a much lower temperature than rock. So the rock has to be thousands of degrees to melt, but ice, we know, melts at 300 degrees, and it's melted. So what does that matter? All right, less heating. You don't need to heat the planet as much, heat the moon as much, and you can make it liquid easier. Okay, but there's another heat source, and the heat source is something known as tidal heating. And I'll tell you now, here, let me show you what tidal heating is. All right, there's no atmosphere on these planets, and so they're pretty much, they don't change with time. Okay, and I'll tell you what they have here. Now, these planets, these are the moons of Jupiter, Io, Europa, Ganymede, Callisto. I don't expect you to memorize them. For God's sakes, it's not important. Memorize it only if you're interested, but it's not required. Saturn has a giant moon. It's known as Titan, and this thing is crazy. It has an atmosphere. Neptune has a giant moon known as Triton. The others have, and there's many small moons on these planets as well. Okay. Io has sulfur volcanoes. Europa has water ice. Ganymede is, we think, somewhat active. Callisto is dead and dirty. And Titan has an atmosphere. And that's pretty neat. And then we'll talk about the atmosphere a little later. Okay. And the nitrogen volcanoes exist on Triton. And Triton's in a retrograde orbit, and it's almost absolute zero out there. It's incredible. 40 degrees. 40 degrees Kelvin is, how much is that? That's 230 degrees negative, Celsius negative. I mean, that's pretty cold. Okay. Now, here is how it works. Here's Jupiter at the center. These aren't drawn to scale. Jupiter at the center, and Io. Io is close to Jupiter, and Jupiter makes a bulge in it. The planet is closer to the bulging of the planet. The tides raised on the planet is dependent on the height. On the radius from the sun, from the moon. The radius from Jupiter makes the bulges here larger, but then it's smaller. All right, now let's go back. All right, now Io moves in concert with the outer planets, Europa and Ganymede, and these have a lot to do with the fact that the Io is held on an orbit that is quite elliptical. And the fact is that going from here to here is like squeezing the planet. Squeeze it, and then you bring it back. Squeeze it, bring it back. Squeeze it, bring it back. Well, that's like taking a ball of silly putty, squeezing it, let it go. Squeezing it, let it go. Squeezing it, let it go. Constantly, for billions of years. What does that do to silly putty or a tennis ball or anything? Squeeze it, let it go. Makes it hot. It gets warm because you put energy into the planet, into the center by squeezing it. The energy comes from your muscles in your arm. Squeezed it. And that energy shows up partly as heat in the center, heat of the object. Io is heated in the same way. But normally, a moon would not stay on this sort of orbit. It would normally be circular, like our moon is circular. It's a circular orbit, and that reduces the heating. So how does Europa still work? All right, now here I'll show you a little bit more evidence. Here's the pizza pie, and here is a volcano. You see the little shadow there? There's a volcano blowing. Now these volcanoes are not volcanoes like on the Earth where the lava flows out slowly. These volcanoes spew, bam, and that sulfur goes all the way out. That's pretty neat, a real volcano. All right, so the tidal force is heating it. The volcanoes erupt frequently, and the sulfur, this is all sulfur on the surface, et cetera, et cetera. All right, here's a blow up of part of one. Just this part here is there, and you can see flows, I guess, of lava on the surface. Now, the question is, we know that Io is being worked over by constantly being massaged by Jupiter. Now, why is it constantly massaged? Is there some reason that's holding? Okay. Now, here is a simulation. These pictures are a simulation of what happens. All right. Now, Io is elongated. Oh, Jesus. Io is elongated. All right, and these other planets have a lot to do. They have everything to do with the reason Io is in this orbit. Okay, so let's play this. All right, the Io goes around, and it's nice and round, 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 as it's orbiting Jupiter, excuse me. And as it gets close to Jupiter, it gets elongated to it. Just like the tides get elongated around when you go around the Earth, except the tides of the moon are constant. These tides are variable because the tidal force acting on it is a function of the distance. Here, its tidal force does heating, and there it's heating, and this now it becomes round, so lets the pressure off. All right, now the question is why? Okay, now let's look at this thing. Now here we see the Io. It's exactly in an orbital phase that is it's aligned. Its phases are exactly twice. The orbit time is twice what it is for Europa. So Europa comes around and bang. See, it was right close. Then it got a little shock there. Here it gets another shock. Now what's happening is that every orbit, every time Io comes around, it's going to be in synchronous, pulled by this one or pulled by this one. So Io is orbiting Saturn in a way, or orbiting Jupiter in a way that is pulled by these little planets and pulled out. And by being pulled out, it means it's in a weaker zone of the tidal heating. And so when it lets it go, it goes in, and then then the tidal heating hits it. But this is orbital resonance that allows this to happen. It's very neat. Okay, so the resonance is 4 to 2 to 1. This is the number of times that Io orbits relative to Ganymede. The number of times Io orbits relative to Europa is twice as fast. And those are what keep it in the orbit. It's pretty neat.
Will it be like that forever?
Yes. Yes, it will, I think. A long time. Now, okay, here's a picture. It's not in color for a change. This is a picture of Io. All right, and the next picture is the same picture, but in the infrared. Remember, the infrared is sensitive to a body's heat, and that'll make it glow in infrared or not. So look here at, for example, this is a volcano, we say, and here's why. Okay? It's exactly at the same spot as a hot spot. Hot spot, hot spot. Those are the volcanoes of Io. All right. And labels, hot spot, just named them all. I don't know why. They might have better names than that, but whatever. All right. Hot spot number 1, number 2, number 3, 4. All right, these are all the hot spots that you see right now. They'll change over time. Ah, shit. Come on. There we go. Okay. All right, now next is Europa. That's Europa. It has metallic crust, rocky mantle, and crust made of water ice. This is sort of amazing. Look at these things. These are blow-ups of Europa. Here, Europa is shown with these huge crusts on it. It's got brown on the surface. This is water ice. But here was a crust. You can see that something slipped. There must have been a fault line here and it allowed it to slip. Now, what you're seeing here is ice. That is the ice on the surface of Europa. And the ice gets pushed together and pulled apart at times, depending on what the tidal forces are doing. As it's pulled apart, some material can flow up from the liquid ocean below. Pushed together, you see it that way. So this is where there's a crack on Europa, and all this material is showing the part that's pushed up. Here is a ridge of pushed up junk. Ice. Okay, it's an amazing tale. You know, nobody had any idea it was going to look like this. It's beautiful. Jumbled icebergs, and the subsurface ocean has to be there. And the magnetic field of Europa is due to salty ocean water beneath the icy crust. Okay, now, where there's liquid water, there could be life. It'd be neat to see it, but I don't know how we're going to get there. It's be very expensive. All right, and here's another picture of it. Blow up a little bit. Amazing. You can see the huge cracks. These are all cracks in the ice. Okay. Now, oh, by the way, The trouble is, nobody really knows how thick that ice is. It could be 1 kilometer thick, 10 kilometers, 100 kilometers. We're just not sure. Unless we are sure, I don't think we want to send a probe to see if there's life on the oceans. If you know, what you could do is land on Europa. Then you could set out a drilling rig. Okay, how would the drilling rig work? Well, you can't turn a drill and have it think it's going to go down a mile or two, or 100 kilometers through the ice. What would you do? Well, what you would do is take a radioactive, this is really bad. You take a radioactive source, like a bomb, and as the radioactive material comes close together, it starts producing tremendous heat, and that heat would then melt the ice. It's tethered to something on the top. It goes through the ice, digs a hole in the ice, and you have a water hole through which you put a probe. Somehow you go in there and you look around with your light or whatever the hell you look with, or something that picks up. You might see, you're hoping to see swimming objects. But life could exist. And the existence of life is, for example, you have energy that could make it there. The energy could be just like the bottom of the sea, where there's these thermal vents at the bottom of the sea where hot water comes out, and bacteria live there. It's a primitive bacteria. It's way down on the tree of life. It's a different branch. It's a thermophilic bacteria, namely one that likes hot water. And they could exist underneath at the bottom of the ocean. It'd be pretty neat to see them. You want to see, unfortunately, I don't think it's going to happen. It's going to be too much money, so they won't do that. Okay. Besides, I don't think they'll do it. All right, Ganymede. Look, this is Ganymede, and here's a picture of this. Here is this and this. Now, these obviously were made at different times. Now, how can you tell that this surface is a lot younger than this surface? How do you know? Yes? The craters have been smoothed over. You can say, look, these craters are markers dating from the time it formed. Here, there were a lot more craters all over the place. Here, there's a few, meaning that the first surface formed a long time ago. We're not sure when, but clearly the differentiation of the surfaces is important. The same is true on the moons of our moon. We have craters all over the top of it. In the seas, which are made of lava, are younger because they have smaller rate of cratering. Okay, the cratering is not intense at the later times. Okay, magnetic field is there. Does that mean it has a subsurface ocean? I don't know, maybe. But you also get radioactive heating from the decay of radioactive products. All right, so here's Callisto, and it shows lots and lots of craters. Now, these craters are white. What does that mean? Well, if you take a hammer to a piece of ice, it shatters the ice. The part that isn't shattered has white structure. You can see the white structure in it. Why? It's because it reflects light differently than the unsmashed piece of ice. So these are where Callisto's been smashed over time. All right, and it has an old surface, dirty ice, no evidence of tectonics, and it's rock mixed with ice, no tidal heating. It has a magnetic field, and it might have a subsurface ocean, but that's just a guess. Nobody really knows. Okay, so here are our moons again. And compared to our, no, that's not compared to nothing. Okay. All right, so there are our moons. Now let's go on. That's the end of Jupiter. Okay, there's a lot you could say about Jupiter. That's it in this course. Jupiter is just a planet. Okay, so now here's this is a picture of Saturn taken by the Voyager as it went by. And Saturn is the planet that has magnificent rings. What are these rings is the first question you ask. Okay, the density is 9.5 astronomical units. Radius is about 10 times that of the Earth. Year takes 29 days to go around the moon. Its density is 7/10 gram. All right. This is Jupiter, or Saturn, excuse me. And Saturn has the rings that tilt because the planet orbits around, and as we see it orbiting around, we can see different tilt axes. All right, so now they're more edge-on than otherwise, but these are the views of Saturn with its tilting rings. All right, now I told you about the Cassini mission, which went to the inner planets, Venus. Remember this? Cassini first went into Venus, then out to Earth, and then it got to Jupiter, and then it went to Saturn. In 2004, it arrived at Saturn. So let's look at what it showed us. All right. Come on. All right, so again, it's like Jupiter. But what are the rings made of? The rings are not, people have guessed what the rings were. They thought they were iron, or they were rings like this ring or something, but they're not solid. They are not solid objects, and they're mostly made of ice and dust. Ice and dust makes up the rings. Okay, now what we think happened is this is material that got smashed on the way into Jupiter, on the way into Saturn, and formed a ring. It never formed a planet. This is, and it may not be permanent. It may go away someday. Okay, all right. Now, there are 4 or 5 rings. Cassini's mission, division, because Cassini wrote about this a long time ago. All right. So he gets to name something. And there are actually 100,000 rings, 20 meters thick. Now, to get an idea, hold a piece of paper, make the paper go from here to Stanford or San Francisco. It's a pretty thin piece of paper. That's how thick the rings are compared to the moon. Piece of paper extending all that way. It's pretty crazy. It looks thick, but of course you can't tell. All you can see is it looks bright. It absorbs the light. You don't know how thick it is. But when you get up there, you realize it's not thick at all. It's very, very thin. Okay. And now Saturn radiates 2.5 times as much as it receives from the sun. That means there's a lot of internal heat that flows out of Saturn. Okay, magnetic field and all that stuff. Here's Saturn. Now this is taken by the Cassini mission. By the way, where's the sun in this picture? Yeah, it's over here, way over there, right? Because it's casting a shadow this way. All right, and this is a website you can go to and see lots of neat stuff, and I'll show you some of that later. All right, here are some pictures. These are by Voyager, actually. These are the rings close up. This is what they think a ring. Oh, well, we know a ring looks like this. It's just a cloud of a whole bunch of snowballs, big and little, a big size distribution. Some of the balls are small, some are big, but that's them. That's the snowballs. All right. All right, here is one from, this was taken by Cassini. Pretty neat. Look at all those rings. And I saw this and thought, gee, this looks just like a 33 RPM record. Now, you guys haven't played with 33 RPMs anymore, have you? Man, are they out. They are gone, gone, gone. I still have a collection of several boxes. And, you know, I have Cream and Jimi Hendrix and the Beatles, all the original stuff. At least you can see with an album, a big album, you got a nice big picture. You can see, you know, the pretty picture, nice picture of the Beatles walking across the street or something. And inside is a phonograph record that looks pretty much like this. Of course, the phonograph record is very thick relative to the thickness of the rings, but it looks similar. Okay, these rings with the gaps are caused by the fact that there's a bigger moon that's in there. And the bigger moon, it's not a big moon, but just a little bigger moon actually shepherds the ring material and causes it to evacuate or push itself into a ring. So I'm not going to talk about that, but that is what it shows. And you can see these moons if you look for them. All right. Now, here's Titan. Okay, this is Titan as we saw it by earlier things. You can look at it. Okay, what does Titan feature? It's the largest of Saturn's moons. It has a thick atmosphere. The atmosphere block, of course, we can't see through it. And it has oceans of ethane. I mean, really, it's crazy. That's a moon such that if you threw a match into it and there were oxygen, there's no oxygen in the atmosphere. But if there were oxygen in it, the whole thing would boom. A hell of an explosion, but there's no oxygen, fortunately. So that doesn't happen. All right. And here, okay, let me get back to that. Okay. All right, this is that web page I pointed out. And there are lots and lots of things on it. Oh, yes. Right. Damn it.
Saturn's mysterious moon Titan is one of the strangest and most Earth-like places in our solar system. Larger than Earth's moon and the planet Mercury, it's the only moon in our solar system that has clouds and a dense atmosphere, mostly nitrogen and methane.
Can you hear that?
Titan's surface remained shrouded in secrecy below the clouds until July 2004. That's when NASA's Cassini spacecraft arrived at Saturn. With its radar and infrared imaging instruments, Cassini was able to lift the veil on Titan. What scientists saw on Titan's surface astonished them. Here was a world that looked a lot like home. Its surface is complex and varied, with Earth-like features, like riverbeds,
Riverbeds, that's
vast
amazing.
deserts covered in dunes,
The beautiful
and
dunes.
hydrocarbon lakes. These are the first open bodies of liquid found anywhere besides Earth. On January 14th, 2005, scientists got an even closer look. The Huygens probe, built by the European Space Agency, parachuted through Titan's atmosphere, taking detailed measurements. The probe survived for several hours on the surface of Titan and returned stunning images.
These were taken as the probe was descending. This was on Cassini.
In spite of their apparent similarities, the differences between Earth and Titan are even more extreme. If you stood on the surface of Titan, the pressure would be like standing at the bottom of a swimming pool. The temperature is minus 289 degrees Fahrenheit, far colder than Antarctica. While rocks on Earth are made of silicates, the rocks of Titan are made of water ice. While Earth's lakes and rivers are filled with liquid water, Titans flow with liquid methane. In fact, there is so much methane on Titan that if free oxygen were also present, a single spark could cause the entire moon to erupt in flames. Most scientists agree that life as we know it would be unlikely on this bizarre world. But the study of Titan will help guide the design of future missions like Terrestrial Planet Finder that are designed to search for Earth-like planets beyond our solar system. The exploration of Titan has only just begun. Over the coming years, Cassini will fly close to the moon several dozen more times, gathering additional data and images and unlocking more secrets of this strange new world, an alien Earth in our own solar system.
Pretty neat. That's only one of the many videos you can find on this webpage. So if you're interested, you should look at it. Okay. Come on. I'm trying to get this voice off. Maybe I'll just unplug it. Okay. All right. This is an outer moon of Jupiter called Mimas. Here's a beautiful bullseye. Bang. That's quite a collision it suffered. This is, and here's craters on it. It's pretty amazing. These pictures, these are incredible pictures that were taken. Here you can see evidence of flows or something cratering over here. It's an amazing picture. All right. Now, first of all, I want to go back. Did any questions on Titan? Titan has, that is not water. Remember, she said the rocks of Titan are ice. Those are ice cubes. That it looks like rocks, looks like granite of our rocks, but it's not. It's different stuff because it's cold enough to make ice the building block of the planet. And the material in the lakes is not water, it's liquid ethane. Man, is that crazy. It's astounding to think about this stuff, what's going on in these moons. And it's all possible because the planet is so cold. If it gets cold enough, you could do this crazy stuff. But I think most of us, I don't know about you, but I'd say life is not possible in these circumstances. It would be a really strange life that it could exist at such a low temperature. It certainly wouldn't be like us, water-based. There's no way we could survive there. We are frozen as soon as you get there. All right. But it's pretty neat. And so that's one thing you learn with these magnificent missions. Cassini tells us a lot. Okay, now Voyager kept going. One of the Voyagers was kicked out of the orbit, out of the ecliptic plane. The other one kept going. And this is, and it went as far as Uranus and Neptune. All right, here's Uranus, and it's got a ring too. It's about 15 times the Earth's mass, 19 AUs, about 4 times the radius, blah, blah, blah. Spin axis is tipped 90 degrees relative to its orbital axis, whereas we're tipped 23.5 degrees. Jupiter is only tipped a few degrees, 2 or 3 degrees, I guess. But this is tipped by 90 degrees, and that needs some explanation. We're not sure why. Probably it had a collision early on in the universe, in the lifetime of the solar system. All right. The magnetic field is tilted relative to the spin axis. It's just like the outer planets, or the inner planets, sorry. 60 degrees at the top of the atmosphere. Really, really cold. Again, that is heating from the sun, balances the heating from the moon, the heat released by the moon. And the sun does not provide very much heat at that distance. Okay. All right. These rings were discovered, but now you can barely see them. And the reason we know that there are rings there was that Uranus passed right in front of a star. Right in front of the star. And while it was doing that passing, people looked at it with a telescope on Earth. And it blinked, blink, blink, blink. And that told them something is obscuring the light. That something was a ring. So they detected 10 rings from the Earth without being able to see them. It's pretty neat to do that. Light blinked on and off. Okay. All right, saw 15 moons in total. This is just before the Challenger accident. None of you were born again. What was the Challenger accident? Yeah.
Space shuttle, like, blew up in the top.
Yes. Right. The space shuttle it went up, and it blew up several miles in the air, and it blew up because of a design flaw in rings that held the hot gases away. They made a design flaw. That combined with the fact that it was very cold in Florida that day, and they have rubber rings like an O-ring, something called an O-ring, and the ring got very stiff. If it were warmer, the ring is more flexible, and there would not have been this accident. But they didn't know that was going to happen, so an accident. All right. Now, Miranda. Well, let's look at Miranda. This is a crazy, crazy moon. Here's Miranda. This one is wacky. Here's an old cratered surface, and here is right here is a different type of surface, and it's got this irregular shape here. What do you think happened to Miranda to make this? Any ideas? I think, I'm not sure this is right, but I think this is the result of a collision by two moons, one of which was a different shape than the other, and when they collided and stuck together, this is what resulted. Of course, they became spherical just from the fact that all planets are spherical. I don't know. That's the best I can guess. All right, here is Neptune with a giant spot. Okay, this storm, I don't know what that is. And these clouds are pretty much like cirrus clouds on the Earth, whipping around this storm. Okay. These are the last of the giants. Planet 8. This thing has 8 moons. The radius is 4 times that of the Earth. A year takes a long time, 165 days, 165 years. Its distance is 30 times that of the distance from the Earth from the Sun, 30 astronomical units. Okay. All right, 17 times the mass, blah, blah, blah. All right, now the reason Neptune was discovered was that scientists were looking at Uranus, and Uranus seemed to not quite obey Kepler's law. It didn't obey Kepler's law quite. It was just a little bit off. Now, if it's off, there's a reason for it. It was off because of the tug from Neptune. Neptune tugs it. The planets don't obey Kepler's law exactly. They tug each other. But this one was tugged as well, and it pulled it off of the Keplerian prediction. And they put it in and said, well, maybe there's an outer moon beyond Uranus. They figured where it had to be. They solved the equations. It's a very tricky business. But they said, well, if Neptune is over here or something, it should be there. And people looked for it, and they saw it. How do you look for a planet in a telescope? It looks just like a star at distance. How can you possibly tell? No, you already answered questions. I got to ask somebody who doesn't know. Sorry about that. Anybody? Yeah. Yeah, that's what you do. You take 2 pictures, and the planet will move relative to the background light of the other stars. They provide a good background, and you look at it, you blink 2 pictures against each other, and see one of these has moved. That is a planet. And that's how you know it's a planet. Okay? All right. It's just like the other gas giants, more or less. And finally, there's a moon that Voyager saw. This is one of its moons. It's a nice one to look at because it looks like a cantaloupe. See? Cantaloupe terrain. Big cantaloupe out there. It's pretty cold, though. All right. And this thing orbits in the wrong direction. It's very inclined, and it's probably not born with, it probably was not born with Neptune. It probably was captured by Neptune later on. Okay, so that was the thought. And that makes, anyhow, that was Neptune. All right, thin nitrogen atmosphere, it's just crazy. All these planets doing something different. And volcanic activity, you know, think of this volcanic activity that emits nitrogen. That's the volcano. Nitrogen in a gaseous form comes out of the volcano. I mean, these things, and this is all possible because everything's so different there. All right. Now, this was August 20. What is that? All right, this is the orbiting time around Neptune. Saw this great dark spot. And the clouds were, all right. So these are some of the moons of Neptune, etc. The Triton, for example, is really cold, 37 degrees. Now, some of you probably play with liquid nitrogen. Who's played with liquid nitrogen? Okay, some of you have. What temperature is that? 77 Kelvin. There's a guy who knows. 77. I wasn't sure. All right, 77 Kelvin. You said that sounded like you said that with knowledge. All right, 77 Kelvin. This planet is half the temperature of liquid nitrogen. Can you imagine an entire moon that has a temperature less than that of liquid nitrogen. It's really wild, very different. Okay, let me just finish now. I've only got a little bit. All right, and that was the end of Voyager's 12-year odyssey. A wonderful trip, and everybody enjoyed the pictures that were sent back all the time. People were tuned into it, and they wanted to see those movies. Now, the only thing we haven't visited is Pluto. And why didn't we visit Pluto? Well, it wasn't easy to get there. And it was predicted. Anyhow, Pluto is an anomalous object. Pluto, first of all, Pluto is so eccentric, it's such an eccentric orbit that it sometimes is closer to the sun than is Neptune. Pluto is supposed to be further from the sun, but it's not that. It's in an eccentric orbit. It's not in the plane of the galaxy. It's tilted from the plane, and sometimes the orbit brings it in closer to the sun than Neptune. That's not very good for a planet. And there's other things as well. Mass of this thing is tiny. How do we know the mass is so small? Well, it's because of this moon that orbits around Pluto, and we can see the time it takes to orbit around in the distance, and thereby measure the mass of Pluto. And so we get the mass, and that's why we say it's a small mass. Okay, and there are hundreds of planets just like it. So the idea is, we accidentally discovered it. It wasn't really. It's not a planet. And if we want to name them all, they could be planets, but they're not. Okay, I think that's the last slide. Yes, it is. Okay, I'll see you on Thursday, and we're going to talk about comets striking the Earth and otherwise.